Ladies, gents, this is 3.1 and 3.2. We're looking at linear and quadratic equations, or the relationships between them. It is Friday, February 28th, 2020. Funny story, this year, 2020, divisible by 4. Gives you a leap year. So tomorrow is actually the 29th. That's random. Anyways, it is, let me get a good color here, Mr. Benjamin. Happy face there because I'm always smiling, I'm always happy. And this is based off of the grade 10 Ontario curriculum. Learning goals for this lesson, we're going to discuss the differences between linear and quadratic equations. Now, just a quick recap. Linear equation, that's your y equals mx plus b. You can see that a lot in grade 9, sometimes in grade 8, and it continues on in the grade 10, but then we eventually get to our quadratics. They have a different formula. Y is equal to ax squared plus bx plus c, and it looks a lot bigger and a lot freakier, and it quite frankly is, but don't worry about that too much. We're also going to identify the properties of quadratic equations. Quick recap on linear equations. Keep in mind, equation y equals mx plus b. Things you want to know from that. What does b stand for? This is your y-intercept. Kind of looks like y-intercept, which isn't a word, but I think we know the difference, right? Our m value, this is our slope. This will all make sense when we get down to the graph too. The data from a linear equation comes from the x and y values, primarily the first differences. When you consider the graph of a linear equation, your options are going to be, or what you'll end up with, is a positive correlation or a negative correlation. So if you have any graph going upward, doesn't matter the degree, it's going to be positive. Any graph going down is going to be negative. For a quadratic equation, slightly different. You still have the same base equations, at least it's similar, but y is equal to ax squared plus bx plus c. So things to keep in mind here. This first value, this will determine the orientation of the graph. Orientation, which we'll talk about in the next slide. The other values for now, I mean, these are both involved in shifts. But don't worry too much about that, okay? The data from a quadratic equation still relies on the x and y values. So on your normal graph, you're still going to have an x and a y. But the determining factor is going to be the second differences. Okay, so we say quadratics are second degree. Put that arrow here. Because of our exponent on our initial x unknown variable. When we talk about the graph of a quadratic function, you have two options. The graph can either open up or open down. And I actually said that in the reverse. This is the graph opening down, so this is a negative correlation. And the graph opening up is right here. It's positive. So if your a value, this here will be ax positive, and this here will be ax negative. And that'll all make sense when we do some examples. But keep in mind, if you have a negative correlation or a negative equation, it's going to open down. And if you have a positive equation, it'll open up. Positive, happy, smiley face. Negative, maybe sad. Hope everyone's happy out there today. Properties of the quadratic equation. So this is our base equation for quadratics. Y is equal to ax squared plus bx plus c. The orientation, as we just mentioned, is based on the second difference. That's going to come from this value. So positive will open up. Negative will open down. And that is, again, based off the second differences. So if you have a table of values set up with x and y values, I'll draw that here. When you look at all of your data, whatever it is, you can look at first differences and then second differences. The second differences, if they're consistent, you know it's a second degree. You'll know you'll have that exponent associated with it. The vertex. Now this visuals tend to help with this. So I'm going to draw two graphs here. This one will be opening up, and then we'll draw another one down here opening down. Actually, you know what? I'm going to draw those a bit differently. I'm going to draw this one right here, and this one maybe here. So keep in mind, positive, negative. The vertex, also known as the optimal value or max or min. The reason for that is that the vertex is the either highest point of the graph or the lowest point in the graph. When it is the highest point of the graph, it's known as a max. So that's right there. When it's the lowest point, it is a min. And that makes sense based off of the data. The axis of symmetry, also known as the midpoint of the zeros. Zeros we'll talk about right after, but what you want to imagine is an imaginary line going right down the middle of either the max or the min. And that will create an effective sense of symmetry between the two graphs, or between the 2 points on the graph. One thing that I haven't mentioned this whole time is you'll notice that all quadratics have circular graphs. Technical difficulties there. Last thing I said was all quadratics have kind of curved graphs. These are known as parabolas. That's just the name for the graph. Either opening up or opening down, doesn't matter. The zeros, it's the point at which the graph passes the x-axis. And odds are you'll have 2 zeros. You can have situations where you have no zeros. For example, if my graph kind of looked like that. So in that case, no zeros. But otherwise, you'd have 2. To do a quick example, now examples are going to look different. Sometimes you'll have a graph, sometimes you won't. Let me draw a graph here, and we'll kind of sketch in as we go. So the zeros, we just said the zeros were the point at which the graph passes the x-axis, are 0 and 9. So both of these, keep in mind, are x values, okay? It's not a plotted coordinate, it's just x and y, or it's just x. The second differences are positive. Second differences being positive, that means our orientation opens up. So if I were to draw a quick graph would maybe look something like that, okay? Based on that, we know that this optimal value, let me redraw that here, is going to be a min. And that will probably come up later in the question. Oh, look at that. Is it a max or a min? Oh, man. Since positive a value, we know the optimal value is a min. And again, you can see that from the graph there. Equation of the axis of symmetry. So if we look back, we said the axis of symmetry is the midpoint of the zeros. So I'm going to write midpoints of zeros. So how do we find the midpoint? Well, we have 2 points, 0 and 9. So maybe we can take the average of them. 0 plus 9 divided by 2, and that would equal 9 over 2. We're going to keep it in a fraction form because it's easier to work with later. Now, the minimum value. How can we actually find the minimum value? Well, the minimum value always occurs at axis of symmetry. And we know the x value for that is 9 over 2. So, if we're given the equation y is equal to, x squared minus 9x, what is the min? So all we have to do is sub in min coordinate, which we found was our equation of symmetry right here. So x is equal to, let me change the color up here. I'll write out the equation. Y is equal to x squared minus 9x. X is equal to 9 over 2. So it gets kind of messy here because we're going to have fractions being squared. Oops. What are we going to end up with here? So when I multiply this out, that becomes 81 over 2. And this, when I square it, it becomes 81 over 4. If I keep it, yeah, that actually works. If I subtract these two. So I'm actually just going to keep this. All we have to do is subtract these exponents. And we know when we subtract the exponents, we're going to end up with the same value because it's just 2 to 1. So it would just be 81 over 4, but it's negative because our negative value is there. So the optimal, I spelled that so wrong. Value is 9 over 2, negative 81 over 4. So that would be the actual value itself, the negative 81 over 4. And we did say it's a minimum, right? So it makes sense for it to be a negative number, so we're good there. Now, I always say thank you with a big happy face. Hope everyone has a great day.